So this is the second video in 3 videos on relative velocity. This is going to be a computational example which will build on a conceptual example I gave in the previous video. So make sure you watch that previous video all the way to the end and make sure you understand that stuff at the end before trying this video. Okay, so we have an airplane pilot sets a compass course due west and maintains airspeed of 120 miles per hour. After flying for half an hour, the pilot is over a town that is 75 miles west and 20 miles south of the starting point. We want to find the wind velocity. Okay, let's start drawing this very carefully. We'll put in coordinate axes. Okay, so x and y axes as usual. We will have the plus x direction be the same as east, plus y direction be the same as north, and then west and south as usual. Okay? So let's start going through the information we have. The airplane pilot sets a compass course due west and maintains airspeed of 120 miles per hour. Now remember, according to that previous video, this information is not giving you the speed of the airplane or the airplane's direction of motion as seen by somebody standing on the ground. Okay? This gives you the motion of the airplane through the air. If the air is also moving, as it is in this problem, the motion of the airplane as seen by a ground observer would not be this, it would be something else. Right? Here's another way to think of this. Let's say we have a balloon here. This is a balloon. And we have an ant that lives on top of the balloon, right? This balloon moves with the air. If the air moves west, the balloon moves west. If the air moves south, the balloon moves south. The balloon is just fixed to the air, okay? Now, what this is telling us is that if we have an ant living on top of the balloon, the ant sees the airplane moving west at 120 miles per hour, right? Or, for example, let's say the balloon is moving south towards you. If the balloon's moving south towards you, the balloon could still see the airplane moving west, even though neither the balloon nor the airplane is actually moving west. Okay? So that first information is just giving the velocity of the airplane with respect to the air, or in other words, the velocity of the airplane as seen by something like a balloon, which is itself fixed to the air. So let's go. Oops. Okay, so to put this in, we'll draw in this first relative velocity vector. This would be the velocity of the plane with respect to the air, which is pointing towards the west. And airspeed here, that gives us the speed at which the airplane moves through air. In other words, 120 miles per hour. Miles per hour is the magnitude of this first relative velocity vector, velocity of plane with respect to air. Okay? Now let's try and use the other information in the statement of the problem. Let's say that the airplane starts at an airport over here at the origin, and half an hour later, the plane is going to be over a town which is 75 miles west and 20 miles south of that airport. So let's mark a point which is 75 miles west and 20 miles south of the airport. Okay. Let's come 75 miles west, that would be an x-coordinate of minus 75 miles. And then 20 miles south, that would be a y-coordinate of minus 20 miles. And then come to that point and mark in a town. Okay, so the airplane is flying from the blue airport to the pink town, and it's going to get from here to here in half an hour. Yes, the airplane is pointing to the west and flying westward through the air, but we have a wind, and so the airplane ends up going in this direction with respect to the ground. Okay? So let's say I put in a direction. Let's say I put in a direction along the ground marked from the airport to this other town. As seen by an observer on the ground, the airplane is moving this way along that dashed line connecting the airport to the town. In other words, the velocity of the plane with respect to the ground is a vector pointing in this direction. Okay, so here's velocity of plane with respect to ground. Okay? So to act that out with my airplane, right, the airplane points itself west. If there was no wind, the air would simply fly west. Right? However, we do have a wind, and we can tell the wind is at least partially blowing to the south, maybe southwest, maybe southeast, but the wind is at least to some extent blowing to the south, which means that even though the airplane is pointing to the west and flying westward through the air, the motion of the wind means that the airplane moves along this direction with respect to the ground. Okay? So this is the direction of velocity plane with respect to air. This is the direction of velocity plane with respect to ground. Okay? Now we would like to find the wind velocity. The wind velocity is the velocity of the air with respect to the ground. Now, how can we get velocity of air with respect to the ground in this figure? Well, remember the sandwich rule that I discussed in the previous video. Okay? We can apply the same principle here. We have three things, right? Airplane, air, and ground. Let's denote the letters. P for plane. Right? A for air, G for ground. Right? And let's apply the sandwich rule here. Right? According to the sandwich rule, we can write velocity of plane with respect to ground. Right? So we're going to take the P and G on the left there. Like we did with the sandwich rule in the previous video, we take the P and G and open them up and drop A's in the middle. So you have velocity of plane with respect to ground equals velocity of plane with respect to air plus velocity air with respect to ground. Okay? The velocity of the air with respect to ground is the wind velocity. Okay? So what we have here is, well, first of all, let's use this to complete the figure, right? What this is telling us is velocity of plane with respect to ground equals velocity of plane with respect to air plus velocity of air with respect to ground. Right? In other words, if we think of this as a vector addition here, I can take velocity of plane with respect to air, add in another vector, and that other vector I add in is going to have to be velocity of air with respect to ground so that this works. I'll show you. Okay, so I come in here, I'm going to connect those up, right? Look at this vector here. I claim that this vector here is velocity air with respect to ground. Okay, how do I know that this is velocity air with respect to ground? Well, my sandwich rule here is telling me that velocity of plane with respect to ground is velocity of plane with respect to air plus velocity air with respect to ground, right? So velocity air with respect to ground must be the vector that fits in here to make the sandwich rule work. Okay? Right, so pause a moment if you like, and then just compare this picture here to the way I've written out the sandwich rule, and you'll see that this set of three vectors combined like so is consistent with the sandwich rule. Okay, so anyways, to do the calculation, we're trying to find the wind velocity, which is velocity of air with respect to ground. So let's solve for that. Right? We have velocity air with respect to ground equals velocity plane with respect to ground minus velocity plane with respect to air. Okay? Now what this is telling us is that if I can get an explicit vector form for velocity plane with respect to air and an explicit vector form velocity plane with respect to ground, I can subtract those and that gives me the velocity of the air with respect to ground, which in other words is the wind velocity. Okay? All right, so first, how about velocity plane with respect to air? Could I take my velocity plane with respect to air that's up here, it was given, and express it in, say, I hat, j hat form? Sure. Okay? Do you remember that any vector can be expressed as its x component times I hat plus the y component times j hat? Right? So just look at velocity plane with respect to air here. You can see that the x component is minus 120 miles per hour, and there's no y component. So we have velocity plane with respect to air equals minus 120 miles per hour I hat. Okay? Now, how about velocity plane with respect to ground? Can we get velocity plane with respect to ground in I hat, j hat form? We can. Here's what we're going to do, right? You remember that for constant velocity, we can express the velocity as change in position over change in time. We can employ that same idea in the vector context as well. So we can say velocity of the plane with respect to the ground is equal to the change in the position of the plane with respect to the ground divided by the time during which that change in position occurred. In other words, velocity plane with respect to ground equals change in the position of the plane with respect to the ground divided by the time interval in which this displacement here occurred. Okay, now, what is the change in the position of the plane with respect to the ground? Well, the change in the position of the plane with respect to the ground is just a vector that goes from the starting point to the ending point. Let's draw that in. Okay? So just draw a vector just from the airport to the town. Okay, so vector that goes from the airport to the town. This vector would represent the change in the position of the plane with respect to the ground. This is the change in the position of the plane with respect to the ground. Okay? And you see that we can easily read off the x and y components of this displacement vector here, right? The x component would be minus 75 miles. The y component would be minus 20 miles. So here we go. Change in position of plane with respect to ground would be the x component, minus 75 miles, times I hat, right, plus y component, which is minus 20 miles, times j hat. Okay? And then the time interval for the process is a half hour. Whoops. Okay, so just do the division, and we get velocity of plane with respect to ground equals minus 150 miles per hour, I hat, minus 40 miles per hour, j hat. Okay, so now we want to finish up the computation and get the wind velocity, right? Remember, the wind velocity is velocity of air with respect to ground, and we worked it out from the sandwich rule that would be equal to velocity plane with respect to ground minus velocity plane with respect to air. So putting it together, we have, again, velocity air with respect to ground equals velocity plane with respect to ground minus velocity plane with respect to air. And if you just substitute these two expressions, just take these two expressions and put them here and here, and you get minus 30 miles per hour, I hat, minus 40 miles per hour, j hat.